network delay time. You are given a network of n nodes labeled from 1 to n. You are also given times a list of travel times as directed edges. Times I value is equals to UI, BI, and WI, where UI is the source node, BI is the target node, and WI is the time it takes for a signal to travel from source to target. You will send a signal from a given node K. Return the minimum time it takes for all the n nodes to receive the signal. It is impossible for all the n nodes to receive the signal. If it is impossible for all the n nodes to receive the signal, return -1. So here in this case, we have this example, the visualized version, and our input times. It says, so this is our list graph, and it's 4. So we can they label from 1 to 4, which is n. K is 2, so that means that we're going to start from K. So here this is what we're going to start from, and our output is 2. So the minimum time it takes for all the n nodes to receive the signal. I'll copy and paste this to keep this in mind. So our next example, example 2 times n is 2, so 1 to 2, from 1 to 2, K is 1, so we start from 1, and we have the output 1. Here times, there's no wait, times n is 2 again, from 1 to 2, and K is 2. So our starting node is 2. And it says there's no way, so we have no way to be able to get this. So we can solve this. So this is shortest path. This is a shortest path problem. This is the Dijkstra's algorithm problem. So now let's make our list. Let's turn our graph to adjacency, to an adjacency list. So let's call it graph list, and will be equals to, so I, so let's make an empty list. So for I, and the and range of 1 to n plus 1 for u, b, w, and times graph list will be u. This is our source node, and then let's add our target node append dot u, bw, and its weight, and the distance cost. So w. So we have this here. So now let's create a dictionary to start distances initialize with float with infinity to for later comparison. So let's call it distance will be equals to, so for oops, let's go float enough for I in range of 1 to n plus 1. So now let's take our distance and distance 0. No, k will be k is our starting node, so starting node given 0 to start of that. So now let's make our min heap. So create min here for the Dijkstra's algorithm heap use. So let's call it min heap equals to, let's make our list and put let's put 0 as the weight and k as our starting point. 0 as weight slash distance and k as our starting point. So while we have a min heap, let's take current distance and then equals to no, we forgot our source node. So current source node so equals to heap q dot heap pop min heap dot so we're going to pop so min heap, oops, yeah, that's it. There's no need to put anything else in it. So once we pop it off, let's check so let's check our if current distance is greater than distance of u, let's continue. If not, let's keep going. So for u, no, v w in graph list u so for u v w guys the let's calculate new distance. So new distance is equals to current distance plus W. So calculate new distance. If new distance is less than our distance here of u, no v, of v, which is our target, or here node, our distance v will be equals to new distance, and then let's push it to our heap. So heap dot heap q dot heap push mean heap, and then let's put our distance that v, and v as our node. So now that's basically it. So let's take maximum time. So max time will be equals to the maximum of heap. Hold on. Maximum of so maximum of the values in our dictionary. So we take this. Okay. Distance dot values. So it will take the value, it will look at the values and take the maximum of them and assign that here. And that's almost it now. So now return the minimum. So this will be done by doing return max time. If max time is less than float dot infinite, else return max time infinity is less than float, else -1. And that's it. So let's see if we have everything that we're supposed to do. So for intervention, UV times graph take u and the distance is equals to intervention distance k infinite. Let's take min heap heap dot q dot path. For infinite distance, if distance is less than this, make this and then new distance, and then if q dot path and then max time. That's it. That should work perfectly. Oops, forgot to make this as a turbo. And that should work perfectly this time. Do you mean hip hop? Oops, missed the P here. and that's it, and it's been accepted. So our time complexity, let me capitalize this, the complexity is equals to O of E, the edges, which are basically edge log n, which is basically the heap function, and this is the creation. So it's actually log n plus n. So our edges is E. This is also for everyone inside it. We just put n, and our heap function here, heap functions is log n. So it's simplified to log n, E log n edges. So now our time complexity, our space complexity, is E plus n. So in this case, we are taking E here, and this is E, our graph, it's adjacency list, and this one is n, and our mean heap also, and that's how we have n. Let's submit to see if it's going to pass, and it's been able to pass all cases efficiently, and that's it for this problem.